Welcome to the HPC Best Practice webinar series. The series is brought to you by the Ideas Productivity Project funded by the Scale Computing Project. The series is a collaboration involving the West Department of Energy computing facilities at the Argonne, Oak Ridge, and Lawrence Berkeley National Laboratories. I'm Osni Marquez from Lawrence Berkeley, Ashley from Oak Ridge, and I will be the host for today's webinar, Color Mapping Strategies for Large Multivariate Data in Scientific Applications. The webinar will be presented by Francesca Samsel. Francesca is a research scientist at the Texas Advanced Computing Center, the University of Texas at Austin. Her research focuses on applying artistic approaches and expertise to real-world visualization challenges. As an example, Francesca is a regular collaborator with the data science at scale and climate ocean ice, sea ice modeling teams at Los Alamos National Laboratory, New Mexico. She's co-editor of the Art on Graphics of the IEEE Computer Graphics and Applications, and she promotes and demonstrates the value of melding art, science, and technology. She holds a Bachelor of Fine Arts from the California College of Arts and a Master of Fine Arts from the University of Washington. We have issued about 200 tickets for this webinar, and all attendees have been muted. We'll be receiving questions through the Zoom chat and also the Google Doc that I pasted. And I'm going to do it again, and that's in the chat. And the webinar will have breaks, so the speaker can respond to the questions that come in. So with that, Francesca, I will stop my sharing here, and you please, it's all yours. Thank you.
Okay, good morning. So is my screen full screen? Are we good?
It's good.
Okay. So good morning. My name is Francesca Samsel, and I'm kind of an unusual, have a unusual background for the DOE. So I just wanted to give you a little bit of an introduction. I started my career painting on the sides of buildings. So I'm kind of running through the background from left to right on this slide. Doing all kinds of large-scale public art. And about 7 years ago, there was an organization that put together some artist in residences at Los Alamos, and I was awarded one. And that's when I started working with the data science at scale team at Los Alamos. There was a DOE program manager that had told Jim Ahrens, who I've worked with closely, that he needed an artist, and I stumbled onto this scene, so that's how that occurred. So we've spent a few years, several years now, many years, working on color to expand what one can see within the data and visualization. And we've moved on a little bit to some other kinds of design elements. And now I've come back full circle on the far right with an NSF grant that is working on using an expanded artistic vocabulary to further improve kind of the amount of data that we can absorb in large-scale multivariate visualizations, three-dimensional visualizations. So that's me in a nutshell. So please feel free questions, and we'll get to them. Oops, here we go. Okay. Color in scientific visualization has there's a lot of research that's been done in that. Traditionally, that has been based on perceptual science, which is very valuable in this case. However, the one area that hasn't been tapped as thoroughly, and that I sort of am one of the people bringing that to the field, is artistic color theory. And artistic color theory has been around for many hundreds of years. So the painting that I'm showing here on the left is 1491. It's Van Eyck, and it's a wedding portrait, and I'll talk about it a little more later. But it is an example of color theory applied to directing attention, to telling you what's important within a scene, what's second most important, and what we don't care about, as well as where we are asking you to focus. So. And then on the right, that palette is applied to visualization. And so we'll get into that further, but that's sort of the basis of the work that we've done here. So just a 2-minute run through color contrast theory in case you're not familiar with it. So this also goes back about 500 years. And there are 7 types of contrast, and they're listed on the left. I'll talk about them in more depth. And what you need to know are a couple things. But one, before we get started, is most folks are used to working in RGB color space, and then there is CIE-LAB space, which is a perceptually uniform color space. So that's good for interpolation between hues. So all of the work that you'll see here is designed in hue, saturation, and value, which is the language I'll be using in this talk. And then it's interpolated in the perceptually uniform space, CIE-LAB, and then it's exported in RGB space so that the computer can digest it. So just a quick run through about what this language and these types of contrast are. The first one is hue, which is simply, is it red, is it blue, is it green? That's basic enough. The second is value, and I don't know if you can see my cursor, but that's just how light or how dark is it. The next is saturation, and that's shown here in the middle with highly saturated colors, which are pure colors without any gray or muted tones. And then the 4 on the bottom are low saturation. So that's a really important type of contrast that we'll be talking about. And then there's complementary and warm cool, which are similar, and it's shown down here. They're opposite sides of the color wheel. And that's a very kind of potent and intuitive color contrast. The cool being yellow, orange, and red. Excuse me, the warm being yellow, orange, and red, and the cool being blue, green, and purple. We're going to skip the proportion because that's a little more complicated, not quite as relevant. But we will be talking about simultaneity as it's really quite relevant and an issue in a lot of visualization. So the first thing you need to know is that what we see, like how much detail, what are the data values that you can see, and what are the features that you can see, are determined by the contrast between the colors, not the colors themselves. And so that's fundamental. And then the second thing that's fundamental is you have a contrast budget. So you want to allocate it carefully. So you can use and throw contrast all over the place, but if you allocate it in the right places, the communication is much clearer. And the other piece of information on this point is, if you think about a symphony, if you've got all the instruments, all the sections, plowing ahead full blast, the drums and the cymbals and whatnot, you're going to have a hard time hearing the piccolo, okay? Whereas if they're quiet and the piccolo's playing, you can hear the violin, no problem. So that's something to keep in mind as we move forward in the talk. Okay. So this is just an example of starting about, this is the same data, okay? And there's a tool that I'll talk about later. This is called Colormaps. It's something we developed with the data science and scale team. And so this is just an example of what one is leaving on the table often if you use a full data range and a traditional color map. This is the exact same data. It's just a different allocation of contrast and hue. And the other thing that's happening here that I'm going to talk about a little more later is, if you notice, the rainbow color map is all fully saturated, okay? And it doesn't contain any changes in light and dark, any changes in value. And changes in value are the strongest type of contrast that we have. Whereas here we take we exploit those properties of hue and value. And that is what is giving you the detail within the data. So the next thing that is important to understand is that colors interact with one another. And I can't overemphasize this because it's not necessarily intuitive. If you put so it's similar to the symphony argument. If you've got a tuba playing, that's going to impact how you hear the piccolo. And so one of the tendencies that we have in visualization is to throw saturated colors on there because we see them clearly and you get more discriminatory power within them, but we don't often understand the cost of the cacophony that's being caused. And so we're doing some research into that area. I'll talk a little bit more about it later.
Francesca, there is a question here.
Sure.
So for those with color blindness, does the hue help?
Well, yes and no. Okay, so there are 3 types of color blindness, and just as a preface, and I'm going to talk about that a little bit later. There are 3 types of color blindness, and the scientific male community has a very high proportion of color blindness, about 12%. So it's a really important issue. So over the years, we have been working and developing and testing color maps, and the ones that we recommend are all tested for color blindness. And the hue has an impact, but what we can do to mitigate that is use value more potently, use it more as one can see here, okay? Because the value and our ability to distinguish between values is not impacted as much by color blindness. It's not that it's not impacted, but it's a way to mitigate. So I will address that question in more detail, but feel free to ask for more details, okay? So in this slide, I'm talking about artificial boundaries and value. And so this is a traditional, on the left, a traditional, rainbow color map. And what is important to realize is that there is no distinction between the data that's yellow, red, turquoise, or blue, or green for that matter. It is just an arbitrary boundary. And so that creates a lot of sort of false attention direction, we call it. And that's, so rather than having those distributions allocated arbitrarily, on the right, what we've done, and I'm sorry, the color scale is not on here. What we've done is we've used the same palette, we've added value, and then the hues are allotted to specific characteristics. So the red is hurricane level. This is sea surface height, and the sea surface height is related to the winds and the level of the wind. So the red is hurricane. So that's the wind.
Other than RPA, probably.
Excuse me?
Yeah. So what's the problem?
I'm hearing several other people. So that's a matter of allocating the hue to the science as opposed to arbitrary allocation. And then the other thing that we're going to talk about is tuning the color and contrast to specific usages. And the issues here, there are 2 issues to talk about. One is there's a principle within color mapping of uniformity. And that means that the contrast is uniformly distributed across the color map. And so there are a lot of color maps that do this pretty well, Beritis and some of the others, but you need to be aware of what you're giving up on that front. And so the rainbow color map, which is widely used, does not do that well at all. But it is used for historical reasons, and that's important to know. And it does show you a lot of detail. It's not that it's all bad in all cases. It's just not what I'm saying. But the most common request that I get from scientists is, can you show me more detail within my data? And so what happens is, either if you look at the top 3 images on the left, either you start with the rainbow. This is the same data. There's no change in the data. Or you hone in on the data range, which is the middle one with the cool, warm color map. Very clear, helps a lot. Often also, though, what people do is they stack the rainbow color map. And then you've got confusion about what data is associated with what. And then you've got the simultaneity problem. What we do is 2 things. One is try and provide guidance on color maps that will address specific needs. And then sometimes we have scientists that are asking for also directing attention and being able to communicate their data. So on the right is an example of how we've used our tool to bring out specific features, so feature resolution and communication. And again, what you see on the bottom is our tool that I'll show you later, which is Color Moves, and which allows us to drop hues in specific data ranges within the data. So for instance, this is magnetic reconnection data, and they were interested in highlighting the location of this specific region over time. So, but they also had wanted to see the waves within the data and the differences between one region and the other. So this is just an example of, if you have very specific goals, there are ways to use color theory to help you tune to those needs. Okay, so kind of moving, so that's sort of an overview. Now I'm moving back down to more specifics. The upper right is a good friend and a wonderful visualization person. And he came to me one day and he said, I have used analogous color, which is another color property that we'll talk about. And analogous color is often used to unify a set of features or concepts. And I said, well, that's really great, Ari, but I would have a hard time living in this space. And so I think this is one of the most critical things that I think we are not aware of on a conscious basis, is that how disruptive this intense color that is to how we can sit and absorb data and be with and explore the data. And I would have a hard time living in the space below. I would have a much easier time living in this, I think it's a Marriott suite or something. And on the right are hues that are pulled from the image on the left. And the point here is that there is plenty of contrast to be had without hammering on all those highly saturated colors. And simultaneity is a property that it talks about how full saturation colors vibrate against one another. And there's research being done now about cognitive load and what that does to our cognitive load. It's still in process, but I think that most people, when they look at the differences, it's pretty obvious. And what I wanted to say here is that the whole painting here is made up of these very, grays, neutrals, low saturation tones. But we can see the detail and get the structure of what's going on, even though they're very coarse strokes. So don't forget your neutral hues when you're putting together a palette. They can also, if you need to provide the saturated hues, they can provide a space to give contextual data on those hues without adding more cacophony. Okay. So to be more specific, this is a data set that was brought to me on the top. The top range was brought to me, and they said, could you help me with this? It's not quite right. And my question always is at the very beginning is, what's the goal? What do you want to see and what's important? And they said, well, the black line is important. And I squinted and I said, which black line is that? So there's a line right here. And what I was told was that the proportion of these specific squares that are inside and outside of that line and the relationships and the proportions are what's important. And then when it becomes a full circle is what's important. And I said, okay, so what we really want to know, I said, is the red cross important? Oh no, that's not important at all. Okay, how about the dark blue? Nope, not important. So the first thing that we do is we took away the saturation from the areas that were not important, okay? And then the second thing is, what's the most important? Well, it's the black line, okay? And the most powerful type of contrast that we have is value. So I went all the way for dark, black line. That's why the newspaper is black and white. And then he said, well, we need to highlight these squares. And I'm assuming you can see my cursor. We need to highlight the squares that the black line resides in so that we can focus and watch them change. And there was a difference between the ones on the corner and the ones that are further in that are brighter yellow. So we used only the contrast we needed, the dark black line, and then to highlight those squares, just put on a light yellow so that you still had the value contrast, but the saturation focused your attention. So the concept is we used only the contrast that we needed. We used value and we used saturation only to the degree that we needed it, but also where we needed it, and it provided a much clearer visualization. Then I spoke about this just a little bit, but being that one of the, by far the most common request I get is more detail from within your data. One of the things we talk about is contrast allocation. Okay, so if you have a color map and it contains a certain amount of contrast inherently within it in terms of the just noticeable differences across the steps, and you know, some are better than others and some are better than others in different regions, but there are a couple things we know, and that is that green has the highest, the widest range of perceptual difference within it. And so often when I'm looking to put contrast in one focused area, I'll use green. And so these, this is just bathymetry data on the Antarctic. But they said, well, what we're interested in is the changes in the bathymetry right on the coasts. I said, okay, here I can't see much of that. Here I can see more. Here I can see some. But if you really want to know the detailed contrast of that region, let's drop the contrast right there, but we're not going to add all the hues and all that other stuff. We're just going to give you a linear color map, which is the best way to interpret scalar value, okay, as opposed to something that moves through multiple hues. So just an example of allocating your contrast to the region where you need it. And the other piece to know, and again, this is our tool, and I will show you how to use it and what it is a little bit later. I'm sure everybody understands about, you know, finding the data range that's most important, but that can often be tricky when you're working. I work in peer review. I know there are many tools out there, but I spend a lot of time with Los Alamos, so I work in peer review, and I'm not as familiar with the other tools, but they work pretty much the same. It's very difficult to hone in on really narrow optimal data ranges. You can say, okay, show me this, you know, you can pull up the histogram and you can say, show me where the data is, and you can hone, you can see here we've honed to the region of where the data is. However, when I talked to the scientists, what they told me was, we really want to see the bow fronts. So this is an illustration of, here's where we have the focal color map covering 100% of the data, and then on the far upper right, it's covering 1% of the data. Okay, so it's much better. But if you really want to hone in, the scientists said this is what they needed, the 42.9 to 44.4. And if you notice, this is 43 to 44.6, and that obscured some of the information that they needed. So whereas it's pretty easy to get to, well, it's easy to get to here, okay, the 43 to 53, because that's where the data ranges are, and you can hone from there. It's in traditional tools, it's much more difficult to get here. So so that interactivity is helpful on honing in to where you're going to allocate that contrast that we talked about before. And so I'll show you how that works. And just so you know that throughout the slides, this is our website down here. It's civiscolor.org, and I'll be talking to you about that a little bit. So then once you've determined where you want to put your contrast, you kind of need to know what kind of contrast or how much contrast or what's appropriate. And this is a concept that, so we're trying to create strategies to provide guidance for this. But this is an example of that same magnetic reconnection data, just a different angle. And they were interested in several things. They were interested in the bow fronts. They were interested in being able to see this region that is, I call them the butterfly wings, although that's clearly not what they are. And they were interested in this kind of detailed region right at the beginning point of the bow fronts. So when I think about that, I think about, here is a combination. Now I know this is red-green, apologies, this is an early section. We usually use red-blue now. But what we do is contextual data is a low saturation map, okay? The lower the importance, then often the lower the contrast value range, which you can see in the dark brown. And then the areas of importance obviously are high saturation. So you've got two kind of different colors from the fire engines, right? And the red they were most interested in that region. So we put the highest saturation, kind of highest attention gathering color map in that region. And then the lime green sticks out right in this region to show small areas. So there's a very difference. You need more contrast or higher saturation if your region of interest is smaller than if it's larger. It's a lot easier to see the contrast in a larger region. So you have to use more contrast to cover small detailed areas. So this is another example of that concept, and it's really helpful when trying to follow features over time. And so this is MPAS ocean data, and it's 6 different time steps. And so they said, okay, the data range that we want to focus on is right here in the center. And we need to know a little bit about what's going on in the abutting region, and we are not too interested in these outer bounded regions. So that's how the type and level of contrast is selected and how different color maps are applied. And so what we're doing at the moment and adding to the website at the moment is putting together sets of color maps and sets of discrete colors that provide guidance for these combined color maps. And they'll show you, like this is for this type of data and this is for this, level of importance. So there's another concept that often gets left on the table when we use default color maps, okay? And that is associative color, and there's a lot of research that says this is incredibly powerful and important for kind of ease of cognitive absorption of material. So this is biogeochemistry data off the coast of California. It's C3SM data, I believe, from Phil Wolfram at Los Alamos. And so this is what I was presented with on the upper left. And what they're trying to do is identify the regions where they could grow macroalgae propagation areas for biofuels. So what are the optimal regions for this specific type of algae growth if they wanted to grow it in the ocean for biofuel? And those have specific conditions. And so we started out just trying, throwing something on there and saying, okay. And they said, well, yes and no. So we moved over, the ocean is clearly blue. It's, that's more associative property. And the region of the algae growth, we want to put green because green is associated with algae. And the red region is where it begins not to be able to be sustainable in terms of a growth area. It's either too far out from the coast or the conditions aren't right. And so we tried a couple of things like optimal areas in number 3, you can see the green. But what we settled on was the number 4, where it shows this is clearly, these are the regions where algae will grow, the green. The red is, nope, that's the end of the story. You're not going to grow any there. And the blue is just contextual. This is ocean, so you get some boundaries. So it's really, they're pretty simple concepts, but they make a big difference in terms of how quickly and readily we can absorb and follow data over time. Okay. So this is a new topic for us, and one that I skirted for a long time, and one that's well studied in the artistic community about what is the affect, not how effective is your color at presenting data, but how affective is it? How do you affect your viewer, and what is the effect on your viewer? And I was interested that one of the requests when I gave this from one of the organizers was to speak about affective color. And the other strange thing is, I think I wrote this publication about 2 years ago. It is by far, like multiple times over, the most read publication I have. And I'm not sure why that is. But I bring it up because There are properties from the artistic community about what kinds of color palettes you use if you want a calming result. So this is on the far left is, it's Manet painting about Monet, or Monet painting about Manet, I can't remember. But it's a calm scene. It's a contemplative scene about the process of this painting activity. And so it's really good, and this is an analogous palette. It's a palette that uses colors that are close to each other, that abut one another on the color wheel. And they're, you might even often think of these as kind of spa colors. They're muted blues and greens and whatnot. They're also natural colors. So that palette is often good for noisy data. So in this magnetic reconnection data, you've got very disparate values abutting one another. And if you've got a lot of high contrast and you put the rainbow color map on this, your eyes just go kind of berserk, because you've got a lot of small detail of highly saturated hues abutting one another, and they vibrate. So I often recommend an analogous palette for noisy data. And then the next image over is interesting. There is from another community, and this is work done out of Simon Fraser University. They talked about what are the associative properties of different palettes. And so what we found was that there's a clear alignment between palettes that artists use and palettes from this more perceptual studies and associative properties. And so that's just another consideration we'll talk about a little bit more, integrating it later. So you saw this painting earlier. I love this painting. And the reason I love this painting is because it really just is very clear about, here's the color, here's what you should pay attention to, and here's what we care about. And so basically there are a couple of different kinds of contrasts going on here. And the first in the upper quadrant here is value. There's a value contrast, and so there's some highlight on, this is a wedding portrait. It's the groom and the bride, and it's commissioned, interestingly enough, by his parents, okay? So you'd think he might be the focal point, but no. So there's a value contrast, there's a cool, warm contrast, and this is number 2. It's also complementary contrast. And then down on the bottom is analogous colors that are close to one another on the color wheel. So what the artist has said is, okay, this is a wedding portrait, and yeah, we know who this guy is, and that's all great, but what do we care about? Well, clearly the saturation is placed on the bed and on the bride. So the message is, what we care about is the next generation. Yeah, these guys are great and all that, but what we care about is the next generation. And they've done that by putting the bed in red, okay, which is the highest contrast. And then they put the bride, who's creating the life, in a fully saturated but analogous complementary color green. And then they've used the analogous colors here to highlight her womb. Okay, and then there are a lot of other elements in the painting that talk about fidelity, and other, these symbols all have very specific connotations from that period of time or meaning. But they're kind of saying, yeah, dude, you're important, but you're not that important. Okay, so that's what they're doing, is they're using color to tell you what's important, to focus your attention on specific regions, and to de-emphasize what is not important. And so those are all things that are really valuable tools in scientific visualization. So we're using that, and my slide's a little bit messed up here, sorry about that. So if you think back to that palette, I had a difficult problem with this. This is Ganymede reconnection, again, out of Los Alamos. And what I was asked to do was, there are all of these little teeny tracks, streamlines here, oops. And they wanted to see all of them, okay, and they wanted to be able to distinguish. I think some are incoming and some are outgoing. I'm not sure, please don't hold me to the science, this was a while ago. But they needed to be able to see the difference. They wanted to see all of them. And then they also wanted to see the background, and again, the properties. You can see this is the same region I had in bright green in a previous slide. It was reversed. They wanted to be able to see that. They wanted to be able to see this transformation, and at that data point, you can see it rests at 0. So it took a bit of finagling, So the lines are small. I had to make them small, the streamlines small, if I wanted to be able to see them individually. So I needed the full range of contrast that I could get. Strongest contrast is luminance, right? So black and white, okay? And then to distinguish the others, the other set of streamlines, I went for a full saturation because nothing else worked. So red, fire engines, full saturation against black and white, which have no saturation. So I used luminance and saturation to make those stand out. And believe me, I tried everything else. It didn't work. And then in order to make the other pieces that they're interested in, the background interested, again, the background, very noisy data. So we used a very simple color palette, an analogous palette, and a complementary palette to enable the streamlines to stand out against the other features. Oh, we talked about that one already. Okay. So those are sort of the principles underlying a lot of our suggestions. And the next thing, I give a 3-hour tutorial on a regular basis for those people that can handle 3 hours. And I often run into these scientists, I'll sound this later, you know, month 2, 3 down the line, and I say, how's it going? How's it working? And they say, wow, that was really a good talk, but I was really interested, it's really important, but I can't make it work. I really paid attention, but I can't make it work. So I said, oh, I got a problem. So, so what we're doing and what we started doing was providing starting points for, so that people have a place to begin to look at their data as opposed to having to build these maps from scratch. So what we have on the bottom here, and we're putting together on the website as we speak, I have a student working on this, are what I call wave color maps, okay? And so they're color maps that have like a divergent is 2, 3, 4, and 5 different linear color segments in them. And what they are is they have specific characteristics. So for instance, this one is a hierarchical map. There's one area, this is of red, that is the focal point. And then the brown or the gray, not so important. And the blue, I want to see this, but it's not as important as the red. And so these maps come in, you know, you can put them in different orders depending on where your data is. And then that's all great, but it doesn't necessarily give you the results that you need. But then you can drop it into, this is Color News, and I'll show you how it works at the end of the talk. And you can slide the regions of what's covered in red or what's covered in blue, and so that you pull out the details with the focal areas that you need. So it's a much simpler, like 1, 2, 3 step process. And there are a lot of waves, and we give you guidance about, you know, this one is if you have one area of focus. This one is if you want equal focus across, but you want more differentiation. Or if you want, you can change the numerical values in the histogram to align with your data. So if you want specific data points, I want from 0 to 1 to be this, you know, specific hue, and I want the focus on 3.2 to 7.8, whatever it might be. So that's the first point. And so, you know, these maps are not good for all data, okay? They really are not. There are reasons to use traditional maps, and there are reasons to use uniform maps when you're like first looking at your data and you don't know what's there or what you care about, okay? These are for the second stage when you're really trying to hone in. And, you know, traditional maps, they work fine if you've got small data and you only need a certain amount of discriminatory power. But as the data sets are growing, we need color tools that are going to enable us to maintain the condensed information, you know, the discriminatory power within the data maps needs to expand to match the expansion of the data sets. And so that's why these tools are becoming more important. So this is that same data. It's combustion, it is fusion combustion data out of Lawrence Livermore. And so these are the 3 most common color maps that are like the defaults that are used today. And they work pretty well. And they're good for a lot of things, but it's important to be aware of what you're leaving on the table. And So one of the things that it's hard to, for instance, if you want to focus on the features here to follow them over time, if this is your color map, or if any of these are your color maps. This is the sequence over time. And I've just zoomed in on the first step for some reason that is unclear to me. But so if you're looking, and I don't know if this is the case, this is just an illustration. If you're looking at following these features over time, you can see how early, mid, and late time steps, like this is the only red area left, whereas here it's expansion. So the focal regions are good for a problem that is common, which is how do you follow features across time when you've got large importance of background. And that background color plays a much larger role than we realize. And what you're looking at here on the top is the same data, and this is with the rainbow color map, and this is with the cool warm color map. And it's important to have the background contrast in the same way we talk about contrast within color maps. So if you look at the lower left, what you're looking at is the blue-gray background for ParaView, the default, as well as the cool warm color map. And the issue is that the blue with the blue-gray does not provide the contrast that you can see on the right, which is simply a dark warm gray. All right. And so the RGB value 107, 107 is something I recommend. It's the stark gray, but you often need to make it lighter or darker, and you can do that by just lowering the numbers, the RGB values up or down, but keeping them the same. So you can see on the back, so the cool warm color map, it occupies the lower end of the value scale. It doesn't have any dark values for good reason, because then it works well on three-dimensional data. So for that, you're going to do better with a dark background and a warm background to contrast, because the red will stand out, but the blue doesn't do too well. Okay. All right. So from there, we're going to move into three-dimensional data. And so this is a volume render data. And if you, I have to get rid of these guys. If you look on the right, it's really clear that by allocating the opacity and where the color map is applied, will give you a lot more detail within the data. But the other thing that's important in volume rendered data is the color map itself, because the colors stack on top of one another. So you can do this a little longer. So this is, I find, and I don't often recommend one color map for all uses, but this it's in our, and on untitled.org, I believe it's like yellow 4 or something, but you'll see it. And because these colors mix well together, and you're seeing, in a volume rendering, you're seeing one color through another, it tends to hold on to the detail within the data pretty well. And so so for three-dimensional volume rendering, I recommend this color map and then a careful tuning of the opacity. Okay, so this is data you may have seen. We did a SciViz, oops, we did a supercomputing video with Galen Gisler on this asteroid impact data. And so this is what they had originally up here on the left, and it's row, and it combines and shows them the different characteristics. But by sort of looking at the color theory behind it, we were able to do two things. And the first on the right here is that we pulled out the structure of the data. So this on the right, we're showing just temperature. We're not showing rho over here, which is a mathematical function that combines the ability to see the pressure, the temperature. And I'm not sure if it includes the water vapor, but here we do. So here we see the blue is cool, obviously, and the red is warm. And then the opacity function has enabled us to see the structures within the temperature, and that was valuable to them. And then when you've got multiple different, when you want to pull out specific features, what we did here was we applied 3 different color maps. And again, we're using a color theory of these are, this is called a tertiary or arrangement, the red, the blue, and the green. And obviously we talked about semantic color or associative color earlier, and the blue is water and the green is land. And the focal point is the eddies as they're moving across the bottom of Africa. And so the opacity function has, has isolated the eddies, but by having 3 different hues that are distinct, then we've enabled them to see the 3 different properties clearly, and you know, it's just as clear as day what's going on. Moving back to the asteroid data. So this is one variable showing structure, and again, it's using one of the wave color maps that we recommend, and the wave color maps are put together to take into account kind of a harmonious color arrangement. And so the reason we're recommending them is because it gets tricky once you start putting different hues and values together. It can be complex. So we're providing recommended wave color maps that are more easily applicable. So this is that data, and I'm gonna stop it for just a minute, kind of midway here. And okay, so so if you look on the right, we have a couple of things going on. We have the water vapor is pulled out, and the temperature is projected on a slice through the data. Okay, so you can get a sense of what's going on with the temperature, what's going on with the water vapor, and early on you can see portions of the asteroid, which is in brown. Okay, and then the other thing that's interesting to the scientists is this is the stratosphere. It's at 700 meters. So you could see the different elements within the simulation. You don't have to condense that into one, but then they and here you can see, like, we created some slices through the data, and the reason that these were of interest was that what they were interested in is determining whether the impact of the asteroid on the ocean would create propagating waves. And so there, down here as it continues, you can see the pressure, whether the pressure waves are canceling each other out or providing propagating waves. But also by dividing things up, what they realized was that there's a large amount of water vapor going up above into the stratosphere, which is greenhouse gas. And so here you can see this is an ensemble configuration showing different runs, but because the hues are intuitive, blue is water and, you know, red is temperature, it's pretty easy to absorb the differences in the ensemble. Okay. And so the properties, you know, the pressure maintains throughout. Like the pressure is still in the reds, and the water vapor obviously is still in the blues. And so you can see and you can follow the properties, even though we're looking at the data in different configurations and for different purposes. So that's why it's helpful to have a color strategy throughout. And I don't think we need to see this. Nope. Okay, moving on. Okay, so this is scivizcolor.org, and it's a website that we developed with the data science at scale team over a course of many years. And it has a range of color maps, different kinds of color maps with suggestions about when to use them. It has color moves, which is a tool I'm going to show you in more detail in just a minute. And then it has color sets, which is sort of falls into that recommended usage category. So more specifically, things are broken down into different types of color maps, and then there are like the recommendations about when you would use different structures. You can see these have different luminance structures. And then there are also they're discrete sets, but also some unusual things. Like down here, you'll see the highlight inserts. So I call these my scanning microscope things. So if you've got a really dense data set and you're not sure where the areas of interest are, there are methods and kind of pre-made sets of things that will help you explore more large data sets in more detail. So this is the interface for color moves. And so on the, and I'll show you how it works in a minute, but on the upper left, there are discrete hues, and then there are a range of color scales or color ramps, depending on what you want to call them. And then there are some other choices below. And so I'll show you how to move your data in there. But then down here, there are pins, and this is your histogram of your data distribution. And you can drop pins in to separate out the data ranges, and you can slide them. You can slide them back and forth. And then these guys, you just click on them and drag them, drop them into the region of data. So you can see it's pretty flexible and very easily manipulatable. And then these slide back and forth so you can find the data ranges that are of interest. So there's a color map here, and it's on our website. You can download it in different formats. And it basically ties the RGB values to the data values. And that's, don't ask me any more technical details than that because I won't be able to answer them. But you simply put that color map on your data and then drag and drop the PNG of that into the interface, the main interface window. And then it'll pop up and look something like this. And then there are the pins, and you can start placing pins in your data, okay? And to divide the color, to divide the data and then drop in different color maps, okay? And there are also, there are some small details, like there are pins, there are little radio buttons on the bottom if you want to get rid of the white, which a lot of people do on color maps. And then you can slide these back and forth to determine what areas you want to emphasize, what areas you want to de-emphasize, where the boundaries are for the color breaks and that sort of thing. So this is what we settled on because they were interested in this combustion data, Jackie Chen, out of Sandia, I believe. So they were most interested in the this really hot region, and the blue surrounds the red in order to help out the colorblind folks. And then the green and the gray and brown can provide context. So you can see that there's a little more focus than here. It's not that it's a world of difference, but when you're working with large data, it will help. So the other things that this tool provides is if you wanted to look at multiple time steps, you can drag in multiple versions, you know, of your data at different time steps. You can drop in different views. So one of the issues is how do you create a color map that works across time steps, as well as works from different angles or different slices, that sort of thing. So you can try out a color map all at one time and see how it impacts the different views and the different time steps. And then once you get something that works for you, you can download. Right here's your download button, and things come out as a PNG, XML, or JSON. And from there, this is the pair view interface, but sure it works similarly in Visit. I just don't use Visit or too many other tools. You just import it, and it'll show up at the pair view at the bottom of your advanced color maps, and then it'll apply to your data. So moving forward, I was asked to speak about what might we want to be considering as tools evolve for scientific visualization, and what are the color capabilities that might be assistants to scientists. And so the things that I have found, I spent a lot of time talking to scientists and talking to them about their needs and how we can help them. And I would say there are a couple of things. One, they need some really easy to use, intuitive tools that are incorporated into the tools that they already use. So Colormoves is an exterior tool, and it's web-based, although if you're in the secure area, you can download the code and use it that way so that you're not on the web with your data, which obviously is not okay. So tools that are incorporated into the workflow that currently exists. And then the second thing is guidance, because it is complicated. And so we're working on that contingent. And then the other thing is easy means of storing and saving the color maps with the data all in one unit so that it can be recreated. And then the other thing is, you know, we're now beginning to talk a lot about the potential for automation. And the automation, there are many approaches to this, and when I was first working with Jim Ahrens and the data science at scale team, I was skeptical that it could be automated, but now many years later, I'm thinking we are ready. And by combining understanding of the perceptual community and evaluating them, evaluating color maps that way and aligning it with the data distributions, there's a lot of potential, as well as with some artificial intelligence and that kind of thing. So I'd be happy to talk to anybody about that. We are working on efforts in that direction, so it's a wide open area. And so the last things I'd say is that color has a lot of potential and to assist in seeing and understanding our data more clearly. And we're leaving a lot of that potential on the table. And then the second thing I would say is that, though, in order not to leave that on the table, we really do need to provide tools that are easy and intuitive and incorporated. And we need to provide guidance. And we need to understand that flexibility, we need to provide flexibility, but not too much. And what is that balance? Because too much, it gets overwhelming. And I didn't speak a lot about three-dimensional data, and I can do that, but at another time or individually if people are interested. But I will say that one thing that we're working on, again, with the data science scale team, we worked on some sampling algorithms in order to begin to use the color schemes on three-dimensional data, volumetric data, but being able to see the combination. So that work is shown here in a little more complexity. So this is MPAS Ocean data showing the waters underneath the Ronne-Filchner ice sheets in the Antarctic. And what you're looking at are 4 different water masses delineated by the points in blue, pink, yellow, and light turquoise, along with the eddies that are moving across on the continental shelf. So this sampling work is being led by Greg Abram at TAC, and we are combining it with the color work in order to provide some capabilities that people haven't had before. And then this is NSF-funded work, which in the concept here, I know this is a bit of a jumbled image, but the concept is that there is, that whereas color has potential, there's also potential in shape and other design tools to assist in these more complex multivariate data sets. And so we are working on tools that are expanding not just the color, but other design elements to help with this more complex data. And the last thing I would say is that when presenting the data, we often leave context on the table and we leave wonder on the table. Science is inherently fascinating. And so especially if we're talking to the public, providing some context and a little bit of like, where does the data come from? How's the data collected? All those kinds of things are helpful in making a more compelling message, especially to the public. And with that, I will be happy to take questions.
Francesca, thank you very much. Yes, we do have some questions here.
Okay.
All right.
Yes.
I think.
Shall I stop sharing, or we don't care? Go ahead.
Yes. So during the break, I think people entered some questions.
Okay.
Okay. So do you have suggestions for visualizing high-dimensional data? For example, six or plus dimensions.
Yes. So I do. And so it depends on what kind of data we're talking about exactly. But what I find most helpful, and I would be happy to do this if there are multiple people that are interested in this question, I find it easiest to answer those questions when someone says, here's what I'm working with, and then I can make some suggestions. I have worked on multidimensional data, and we have used basically color theory to distinguish between dimensions and be able to present that data. There was some work done, drag and drop, oh gosh, out of Los Alamos for multidimensional data. So it's a problem that we haven't tackled a lot, but that we can respond to. And if anybody's interested in a group that might begin to discuss that problem, I would be happy to participate. That's the best I can do for you.
All right, so the next question here. Is it easy to export color maps to ARC? I don't know how to spell this. ArcGIS?
Yes, ArcGIS. So that is
GIS, yes.
yes, yeah, that's a common question. And I do believe that we have someone working on that. These are pretty simple transformations, and we are updating the website. And right now they just export to JSONs and XML files, but these conversions are easy. And in the next iteration, we will be doing R and ArcGIS, and we've had requests for one other thing I can't remember at the moment. And also, if people are interested in doing that right now, there are, if you look on the web, there are conversion scripts that are pretty straightforward because it's just RGB values.
Okay, next question then. Do you have any thoughts about colors that are better to use when lots of data is sitting in the same spot, like a scatter plot with lots of points overlapping?
Yes.
And then the participant continued. I generally adjust the opacity, but are there better colors to use in this situation?
So I'll point you to a couple of tools. There is a lot of work, and this is what's called the information visualization community, a lot of work on perception and cognition on that topic, a lot of research. There's one new tool out, and it's called Colorgorical. It's C-O-L-O-R, Colorgor, G-O-R-I-C-A-L, Colorgorical. It's out of Wisconsin by Karen Schloss, and it's specifically designed for that purpose. And it enables you to kind of put in parameters like, I want this many hues, or I want them to be distinct, or I want them to be different, or I want them to be in this color range. And then it will spit out for you a series of options. And so that's probably the best one I recommend for that. And opacity is really, really helpful in that regard. But there's an entire field of literature on just that topic, and that's not my specialty. But we will have on the updated website some pointers, not just to Colorgorical, but to some other tools that help with that, as well as lit reviews on things, ways to approach that.
So the final question here, I think it's an interesting one. Is it possible to export the color maps to MATLAB?
Yes. Yeah, there is on the website, there's a, like, I don't know, there's a button, you know, and you can say, I want an XML or I want a MATLAB, you know. Or matplotlib maybe is what it is. So these formats are all very similar, and it's a pretty direct conversion script. And I know that right now we have matplotlib, and I don't even know how that varies from MATLAB, but I will take a look, and we're going to address that in the next couple of weeks.
Okay, thank you very much, Francesca. I'll just then share again my last slide here. So
okay, let me stop.
Yeah, because then it's just
what? Oh no.
Right.
Am I still sharing? I need to stop. It doesn't seem to be that way.
No, let's see. I think I was sharing here. Maybe you are sharing.
That's curious.
I don't see your slides, Ozzy.
Yeah, that's what I'm trying to do. So allow.
Oh, there it goes.
Yeah, just for the records then, thank you all for participating again. So we'd like if people could give us feedback about the series, about this presentation. The next webinar in this series is going to be in about a month, September the 9th, testing and code review practices in research software development. And the presenter will be Nasser Isti from the California Polytechnic State University. And we are already accepting registrations for that. With that, I'll stop the recording here.